during my stay here in Korea. Today I'll be talking about conformal blocks for SLN level 1. And a number of us at the University of Georgia are, whoops, what's that?
Oh, you mean next page?
Yeah.
Maybe did not.
Okay. Okay. Well, anyway, I'll just stand by the computer then. A number of us at UGA are working on conformal blocks, and so today's talk represents joint work with Valery Alexeyev and Angela Gibney, as well as two graduate students, Maxim Arap and Jim Stankiewicz. So before I tell you what conformal blocks are, I'd like to tell you a little bit about why I'm so excited about them. And so I'll start out with three questions that interest me regarding the birational geometry of M0 n bar. So the first question is, which Neff divisors on the moduli space of curves M0 n bar are semi-ample? Now, in positive genus, we have an example due to Kiel of a line bundle which is Neff but not semi-ample. On the other hand, many people believe that M0 n bar is a Mori dream space, in which case the answer to this question is every Neff divisor would be semi-ample. But really, to me, that's just a preliminary question for my second question. So suppose you start with a divisor which spans an extreme array of the Neff cone, and suppose you know that it's base point free. Then you could ask, what's the morphism associated to the linear series of D? Okay, and to me, that's the interesting question. I don't just want to know what the Neff cone is, I want to know about the maps and morphisms to other varieties. And my third question reflects my particular taste in algebraic geometry. Throughout my career, I've studied GIT quotients, and many of these are compactifications of M0n. And so I'd like to know which GIT quotients give us new and interesting compactifications of the open part M0n. Now, regarding the first question, let me give you a little bit of history. In the past, one of the main tools for studying Neff divisors has been something called the Ray theorem, which is due originally to Kiel-McKernan and was extended a little bit by Farkas and Gibney. Okay, and the Ray theorem tells you that certain extremal rays of the cone of effective curves are spanned by these F curves. Okay, so if you have an extremal ray of the cone of effective curves, and if you can also find an effective divisor G such that delta minus G is also effective, and K plus G intersects this ray non-positively, then your ray is contractible, and moreover, it's spanned by an F curve. Okay. Now, the conditions that both G and delta minus G are effective forces G to be supported on the boundary with coefficients between 0 and 1. Okay, and so it's an easy corollary of the Ray theorem that if you have a divisor on M0 n bar, which is log canonical, and if you know that your divisor furthermore intersects all the F curves non-negatively, then you conclude that D is Neff, and then of course we can also apply the results of BCHM to conclude that D is actually semi-ample.
So what is delta in that theorem?
Delta is the total boundary, so the locus of all nodal curves. Okay, and I just want to point out that the properties of being log canonical and intersecting all the F curves non-negatively are both convex conditions, and they're also completely combinatorial. Okay, so we get a large subcone of the Neff cone, which we can understand completely combinatorially. Okay. Now, throughout my talk, I'm going to focus quite a bit on symmetric divisors, and there's several reasons for that. First of all, the dimension of the symmetric part of the Picard group grows much more slowly than the Picard number of M0n itself. So we can calculating things is much, much easier. Second, of course, studying symmetric divisors on M0 n bar by the usual incantations is really telling you about the geometry of the hyperelliptic locus in MG bar. Also, by results of Gibney, Kiel, and Morrison, we know that the Neff cone of MG bar pulls back to a subcone of the symmetric Neff cone of M0 n bar. And so those are all good reasons for why we should study the symmetric divisors on M0 n bar. Okay, so let me make a definition. I'll call a divisor symmetrically log canonical if I can write it as k plus boundary, where all the coefficients on these boundary components are between 0 and 1. But of course now I'm using the bi's, and remember that bi is the sum of all the classes delta I, where the cardinality of I is equal to little I. Okay, so this is like being log canonical, but just writing things in a much more special form. Okay, so once again, there's an even simpler combinatorial criterion for a divisor to be symmetrically log canonical. And of course, this is a convex condition, so we're going to get a nice subcone of the symmetric Neff cone. And actually, the Ray theorem is very powerful in this case. So for n up to 11, every symmetric Neff divisor is actually symmetrically log canonical. Unfortunately, starting with n equals 12, you can find symmetric Neff divisors which are not symmetrically log canonical. On the other hand, the Ray theorem is still very successful in these cases. For instance, for n equals 23, you can show that about 75% of the extremal rays of the Neff cone are symmetrically log canonical. Okay, so it's really fair to say that a huge subcone of the symmetric Neff cone can be studied completely combinatorially. Okay, so those are the ones that we've known how to handle for quite a long time. And what I want to direct my attention to is, what about the rest of the cone, the part that's not symmetrically log canonical? What can you say about that? And you could be thinking, okay, well, if we look outside the combinatorial part of the cone, then maybe one of our main tools for studying the rest of the cone should be geometry. Okay, I'll remark on my second question. Log canonical divisors, of course, are semi-ample, but BCHM is just an existence theorem. Okay, so further study is required to identify the linear series of those divisors as, for instance, classically known spaces or moduli spaces. Okay, so even the part of the cone that's combinatorial, we still want to study the maps associated to those divisors. And last, my particular favorite, which GIT quotients are the interesting ones? Okay, so over the past several decades, many people have considered GIT quotients, which are compactifications of M0n. Probably the first and best known is points on a line. You can take P1 to the n, mod by SL2, and of course you have a choice of linearization. But that's not the only parameter space you can start with. You could also, for instance, start with the Fulton-McPherson space, P1 brackets n, and that's been studied, for instance, by Kiam and Moon, who are in the room today. Another parameter space you could start with is something like what appears in my paper with Elizabeth Baldwin or in my PhD thesis. You could start with a locus in the Hilbert scheme, which parametrizes plurically canonically embedded pointed curves. Okay, and again, you have a choice of linearization. Or, more recently, here's something that's been studied. Instead of taking points on a line and modding out by SL2, let's start with pointed conics. Okay, so I have a P5 dual parametrizing conics in P2, and I can look at the incidence locus where my points in P2 land on the conic. Okay, and then I could mod out by SL3, and once again, I have a choice of linearization. So a question that GIT experts need to answer to continue our research program is, which parameter spaces and linearizations will give us new and interesting compactifications of M0n? And the theme of my talk is that conformal blocks can help us answer all three of these questions. They give us semi-ample divisors on M0n bar, which are frequently not symmetrically log canonical. Okay, so they're outside the combinatorial part of the cone, and they're in the part of the cone that we didn't know much about before. Moreover, when you identify a divisor as being a conformal blocks divisor, that sometimes gives you a clue about the image of the morphism associated to that divisor. And we'll see that often those images of those morphisms are going to be GIT quotients. Okay, so in the next part of my talk, I'd like to tell you a little bit more about conformal blocks. I'll outline the construction and some of their main properties. So, when I say the words conformal blocks, what I mean are vector bundles on the moduli space of curves MGN bar that arise from a certain model of conformal field theory called the West-Zumino-Witten model. These were originally constructed by Tsuchiya, Ueno, and Yamada in the 80s. And they're specified by 3 pieces of data. The first one is G, a simple Lie algebra. The second ingredient is a non-negative integer L, which physicists call the level. And the third ingredient is a vector lambda, which is an n-tuple of dominant integral weights in a Weyl alcove for the Lie algebra G. And just to give you an idea of what the level is saying, let me draw a picture for SL2. Of course, everybody knows what a Weyl chamber is. Sorry, yes, thank you. Rank to SL3. You start with a Weyl chamber. Here, for instance, are all the weights of level 3. So Weyl alcove just means truncate your Weyl chamber at some finite level. Okay. So now I just want to give you a hint as to Tsuchiya, Ueno, and Yamada's construction of these bundles. And the point of going through the construction is to show you how cumbersome it is. And I guess what I'm really trying to advertise is I hope that sometime soon, perhaps someone from my group or someone else can give a simplified construction of these vector bundles. So I'll start off by constructing the affine Lie algebra G hat associated to G. So I start by tensoring G with Laurent series and then make a central extension. Okay? Now, the representation theory of affine Lie algebras closely parallels the representation theory of simple Lie algebras. Okay? In particular, to each dominant integral weight, you can associate an irreducible G hat module, which I'll denote by H sub lambda I. Okay, and then the major difference between affine Lie algebras and simple Lie algebras is that this H lambda is generally infinite dimensional as a C vector space. Okay, and then I'll tensor all of these together for my n weights lambda I and get one module that I'll write as H sub lambda. And what I'll try to do next is to describe the fiber of my vector bundle over a point that corresponds to a point in the interior of MGN. Okay, so I'll start with a smooth curve C and some distinct mark points PI. All right, so let U be the open set, which is the complement of the marked points. And I'll choose a local coordinate ZI around each marked point. And in particular, that gives me ring homomorphisms from the set O of U to Laurent series in the variable ZI. Then Tsuchiya, Ueno, and Yamada go on to define an action of G tensor O of U on this module H lambda. And I have very little to say about this formula except that it's completely explicit. Okay, so we have an action of this Lie algebra on H lambda. I need to recall one more definition. So let's say you have a Lie algebra that I'll write as A and an A module which I'll write as W. Then the coinvariance of this action on W, I'll denote it by W bracket sub A. And all it is I take W and I mod out by the span of all the vectors of the form x times W. Okay, so the coinvariants are the largest quotient of W on which A acts trivially. Okay, then the fiber of my vector bundle is just going to be the vector space of coinvariance. I take H lambda, it has an action by G tensor O of U, and I take the coinvariance by that action. Okay, and just for notation, to lighten things up a little bit, I'll denote that vector space as V, I'll record C and the marked points in lambda. Okay. Here are some main results on these vector bundles. The first one is that this vector space that I just defined is actually finite dimensional. Let's take a look at that again. I'd say that's highly non-obvious. Again, this is an infinite dimensional C module, and this is an infinite dimensional group, and so I wouldn't say it's clear at all that when you take coinvariance, you'll get something finite dimensional. But you do. Moreover, these vector spaces fit together when you have curves and families, and they give you an algebraic vector bundle over MGN. Everything I just said was for smooth curves, but Tsuchiya, Ueno, and Yamada show that your vector bundle actually extends across the boundary to give you a vector bundle on MGN bar. The next property is something really nice. If you look at the fiber of these vector bundles over a nodal curve, they emit a very specific direct sum decomposition called the factorization rules. And I'll say more about that in just a minute. But this is a really amazing property that these vector bundles have that really allows us to commute things nicely. The last general property that these vector bundles have is that they emit a projectively flat connection. Okay, so all of these properties that I've mentioned so far are true in every genus G. When the genus is 0 on M0 n bar, you can say a little bit more. In genus 0, we know that the connection satisfies something called the Kinetic-Zelemochikov equations. And we also know in genus 0 that the vector bundles are globally generated. It's an open question whether that's true in higher genus. I don't know if it's true or not. And just in passing, I want to note, do these properties characterize conformal blocks bundles? We'll see especially that factorization is really an amazing property. And I wonder if you have a vector bundle that satisfies this list of properties, if that means that it has to be a conformal blocks bundle. I don't know. And then once again, in genus 0, again, we know that these are globally generated, and I think there's a lot of clues that there might be a much simpler construction of avoiding this whole infinite dimensional construction due to Tsuchiya, Yamada, and Ueno. Okay, so the next thing I want to do, I want to tell you more about this factorization property because we really use it to study these bundles. And I just need to fix some notation first. Okay, so if I have a simple Lie algebra G, I can define an involution which I have no idea if it has a name in the literature, but the physicists write it as star. Okay, and since today I'll only be talking about conformal blocks for SLM, let me just tell you what happens for SLM. There's a set of generators for the root system called the fundamental dominant weights, and they're generally denoted by omega j. And the star of omega j, if you're working in SLM, is just omega m minus j. Okay, so our involution, again for SL3, is just reflect across this hyperplane, and then you send this generator to that one. Okay. In particular for SL2, if you just look at the formula, this is telling you that actually for SL2 this involution is trivial. Okay, so now I can tell you about factorization. So say I have a nodal curve, and let's just assume for simplicity that my nodal curve has two components, one that I'll call C1 and one that I'll call C2, and let's say the point of attachment is X on this side and that it's Y on this side. Okay, and let's say I have a bunch of marked points on this side, so let's say that's PI for the labels I and some set I, and then of course the rest are over on the other component. All right, factorization, I said, is a very specific direct sum decomposition of this vector space. And here it goes. If I look at the total curve, the vector space there decomposes as the following sum. For each weights in my vial alcove, I look at all the possible ways that I could insert an extra weight corresponding to the point X on the C1 side. And then over on the C2 side, I insert the dual weight mu star. Okay? And then tensor all those together, sum them all up, and that's factorization. Okay. I doubt it. So here's a little bit of history. Now, these bundles got a lot of attention in the 80s and 90s, and I can't possibly mention all the people who've worked on them. So let me just mention the few results that I am really going to refer to today. So first of all, in the 1980s, these were constructed by Tsuchiya, Ueno, and Yamada. And in the 1990s, several people worked on something called the Verlinde formula, which, among other things, computes the ranks of these vector bundles. The new ingredient of this, which is so exciting to us, is that recently, just last year, Factorization, who's at the Tata Institute in India, found formulas for the Chern classes of these vector bundles when the genus is 0. Okay, and so we're able to compute examples of these bundles for the first time. All right, and so what I'd like to do now is to outline a way that you could compute the Chern classes of these bundles. I'm not going to do exactly what Factorization does in his paper. I'm going to give you my own point of view, which I believe is a little bit simpler. And also, I'm hopeful that my point of view on things will extend to positive genus, whereas I doubt his would. So first, let me make a reduction step. And this was pointed out to me by Shreeman Kumar. So if you have a vector bundle with a projectively flat connection over a simply connected base, like MGN bar, then the higher Chern classes Ci for I greater than or equal to 2 are actually determined by the first two, C0 and C1. Okay, so it's enough to just compute C0 and C1. The next reduction, if we happen to be working on M0n bar, we know that the F curves span the second homology H2 of M0n bar. Okay, and so that means you can determine the class of C1 if you know the intersection numbers with every F curve. Now, my next reduction is that you can compute C1 of any one of these vector bundles if you know how to compute C1 of every conformal blocks bundle for that G and L on M04 bar, and if you know how to compute the rank of any conformal blocks bundle for that G and for that L. So let me explain that now, and I'll actually work on the board for this, and our main tool is going to be factorization. Okay. All right, so I want to compute C1 of my vector bundle dot an F curve, which I'll write as F, I1, I2, I3, I4. Okay, and this F curve, remember, what does it look like? I have a central spine, which is a P1, and then I have 4 tails, which I'll call C1, C2, C3, and C4. And writing my F curve this way means that the marked points that lie on the tail C1 are points whose labels land in the index set I1. And the points whose indices lie in I2 are on this tail, and so on. And I want to normalize my F curve. And so I'll say that I have my central spine P1, which is attached to points, I don't know why I drew lines, sorry. I'll call them X1, X2, X3, and X4. And then on my tails, I'll assume that the points of attachment are Y1, Y2, Y3, and Y4. Okay. And the last thing I want to do is introduce a little bit of simpler notation. So for each I, 1 through 4, all right, Wi, given us weight mu, to be the following vector space. It'll be the conformal block you would get from the curve Ci with the marked points, let's call it Pj, for j in I sub I. And then, of course, we have the one extra attaching point. And then, of course, I have the weights lambda j for j in I1 or II. And then I'm attaching one extra weight mu. And I'll let Ri mu be the the dimension of this vector space. Okay, then what does factorization tell me? It tells me that if I look at my vector bundle over some point, which I'll call capital P in my F curve, that I get a direct sum decomposition over all the weights in the vial alcove, PL. I get the conformal block vector space for P1 with marked points x1 through x4, and weights mu1 through mu4. Sorry, I'm going to factorize 4 times, right? So I can actually choose 4 attaching weights, okay? And then each time I'm just tensoring with these vector spaces coming from the tails. So I have wi mu sub 1 star, w2 mu sub 2 star, w3 mu 3 star, and w4 mu 4 star. All right, so factorization the way I told it to you applied to just a single point in the moduli space at a time. But now think about our F curve. To sweep out an F curve, what you do is you allow the cross ratio of the points x1 through x4 to vary. And that's what gives you the F curve in the moduli space. As that happens, you can see this conformal block will be changing, right? Because we're changing the relative positions of x1 through x4. So this factor is changing, but these other factors in the tensor product aren't. They're fixed. Okay, and so what that is saying is that our vector bundle actually decomposes over the F curve. So my vector bundle restricted to the F curve looks like a direct sum, again, over all possible mu's and the vial alcove of length 4. I'll write it just as A sub mu tensor B sub mu, where A sub mu is a conformal block on P1. So again, it's V, G, L, 4 weights. And B mu is a trivial vector bundle with fiber given by this fixed tensor product. Okay, so now I'm trying to compute the first Chern class of this vector bundle. Okay, and so I'm going to get the sum of all the Chern classes. I'm only going to get the Chern class here and then just the rank here. Okay, so that means I get this formula. So C1 of V dot F is just the sum of all the degrees of these vector bundles on P1 times the product of 4 ranks each time. And if you think back to Angela's talk this morning, I think this formula is quite a bit nicer than the monstrous thing that she was writing on the board this morning. Okay. So incidentally, all these notes are on my webpage if you want to find anything there. All right, so we've reduced the problem to we can compute any one of these intersection numbers if you compute degrees of vector bundles on P1 and if you can compute all these ranks. So let me tell you how to finish off the problem. So to compute everything on P1, well there, Factorization does an explicit calculation. You have a vector bundle with a connection, and so he just explicitly calculates the residue of the connection in local coordinates. All right, so that finishes that part of the problem. And now you need to know how to compute ranks. And here again, I think the most efficient way to approach things is through factorization. So you can factorize at what Kiel would call a vital point of M0 n bar. So again, this is just a curve whose dual graph is a trivalent tree. And what that'll give you is a recursive formula for the ranks of these vector bundles in terms of ranks of conformal blocks bundles on M0 n prime, where you have a smaller number of marked points. Okay, and so you can factorize, factorize, factorize. Ultimately, though, you're going to have to know the formula for the ranks of these vector bundles when you have either 1, 2, or 3 marked points. And those formulas, again, these came from the physicists first. The set of numbers like this are called the fusion rules. Okay, for 1 point, the fusion rules are pretty simple. The conformal block for P1 with 1 marked point is either 0-dimensional if the weight is non-zero, or it's 1-dimensional if the weight is 0. If you have P1 with 2 marked points, then you get a 0-dimensional conformal block if mu is not the star of lambda, and you get a 1-dimensional conformal block if mu is lambda star. Okay, so for a fixed Lie algebra G, to get any further with computing examples, you have to know the 3-point fusion rules. Okay, and in general, that seems like a pretty hard problem. So what I'll say about that is that we know explicit formulas for these 3-point fusion rules in a few cases. So one case is SL2 in any level. We also have a closed form for the fusion rules for SL3 in any level. And we also know the fusion rules for SLM if you restrict yourself to level 1. Now, for SLM level 1, I can even tell you more explicitly what the fusion rules are. They happen to coincide with the Littlewood-Richardson coefficients in this case. So in general, you can think of fusion rules as truncated Littlewood-Richardson coefficients. In this particular case, SLM level 1, they're actually the same. Okay, so how does that go? Well, like I said before, the weight lattice for SLM is generated by what usually go by the name of fundamental dominant weights in Lie algebra literature, and they're denoted omega 1 up to omega m minus 1. Moreover, for SLM, we know that the weight lattice mod the root lattice is equal to z mod mz. Okay, and so I can identify the image of my omega I with the integer I under that map. And so here are the 3-point fusion rules for SLM level 1. If I have 3 points on P1 with weights omega I, omega j, and omega k, I'll get a 1-dimensional conformal block if the sum of my 3 weights is in the root lattice, or corresponding to the fact that I plus j plus k should be congruent to 0 mod m. And I'll get a 0-dimensional conformal block otherwise. And one corollary of this, if you apply this repeatedly with factorization, you find that for SLM in level 1, no matter what lambda you start with, you can start with any number of marked points, you'll never get a rank that's bigger than 1. Okay, so you could either have a 0-dimensional vector bundle, which I guess is not a very interesting thing, or you might get a line bundle on M0 n bar. And again, remember, they're globally generated line bundles, so we get semi-ample NEP divisors on M0 n bar this way. Okay, now factoring goes a little bit further. If you combine the fusion rules that we just saw for SLM level 1 together with this formula, and also put it together with his formula for the degree of a vector bundle on P1, then you get a nice formula for intersection numbers with F-curves in this case. All right, so I've written it up here. What you do is for each tail, you sum up the weights, and you compute the congruence class mod m of that sum. And then he'll tell you the formula for the intersection number in terms of those numbers. I actually think I'm ahead of time, so let me just do an example really quickly. Okay, let's find, let's start with n equals, sorry, let me look at my notes, 28, I believe. All right, I'll take G to be actually SLN, so SL28. Okay, again, we're taking level 1 for the rest of my talk today. And my set of lambdas, I'll take the weight omega 11 28 times. All right, so I have a symmetric divisor on M0 28. And I want to compute what's, let's write D for this line bundle. And I want to compute what's D intersection with F111 25. Okay, so Factorization would say, start off by computing these numbers that he calls nu sub I. So what do we have? I have 1, 1, 1, and then I have 25 points on my last tail. So nu sub 1, I add up the weight on the first tail. I have 1 point. It has weight 11. Okay, so nu sub 1 is actually just equal to 11. And so are nu 2 and nu 3. My last point, what am I supposed to do? I have 25 points, and they all have weight omega 11. Okay, so I have 25 times 11 is 275, and I'm supposed to find the remainder of that mod m, which is actually equal to n in this case. All right, so 275 divided by 28 is 9, with a remainder of 23, and so nu sub 4 is 23. Then what does Factorization tell me to do? He says, sum up the nu sub i's. Sum of the nu i's in this case is going to be 56. And that's equal to 2 times m. All right? And now, what's the next thing I need to do? I identify the smallest of the nu's, which is 11. And I find the largest, which is 23. And so we see that I'm in the last case here. So the sum of the nu i's is 2m. The sum of nu min plus nu max is greater than m, and so my final answer should be m minus the nu max, which is 28 minus 23, which is 5. Okay, so again, in this special case of SLM level 1, we get a beautiful piecewise linear formula for these intersection numbers. All right, now in general, I want to tell you a little bit about some of the work I've done. I implemented Factorization's formulas in Macaulay 2, and I called this package conf blocks, and it'll be released soon. In fact, next week I'm going to a Macaulay 2 workshop, and I hope that it'll be ready by the end of next week. And what it computes are 3 things. So first of all, you can compute the rank of any one of these vector bundles. Okay, you can also compute intersection numbers using Factorization's formula. And then the last thing it'll compute, if you actually want a divisor class, at least in the symmetric case, it'll compute those. Now, I mentioned the last ingredient you always need to do these calculations is something called fusion rules, and I completely punted on that. I didn't implement it myself. I call a program called CATS, which was written by some European physicists to compute the fusion rules. All right, so we have this computer package, and we were able to compute lots and lots of examples of conformal blocks divisors. And here's an observation that we made from doing that. So we found that if you take SLN level 1 and a symmetric set of weights omega j, then that always seemed to give us extremal rays of the symmetric Neff cone of M0n bar. Okay, and here again, I just want to point out, I'm using SLN, where n matches the number of marked points. Okay, so that's our experimental observation. How would you prove something like that? Well, so the first thing I want to do is figure out the ambient vector space. So we're working in the vector space of symmetric divisors on M0n bar, and I'll call the dimension of that G. And then, of course, you can work out that G is related to n by either 2G plus 2 or 2G plus 3. The next thing I'll do is I'll try to find a family of curves. We're in a G-dimensional vector space, so I want G minus 1 independent curves, all of which intersect my divisor in degree 0. And what that would tell me is that my divisor must lie on, G minus 1 independent facets of the Neff cone, and so it would have to be an extremal ray. Okay. But again, from looking at examples, you see that in general, these divisors tend to intersect lots of curves in degree 0. So this family is almost never handed to you. You have to look at a long list of curves and try to figure out, okay, which subset of these curves might be independent of each other. Okay, and so to select a family like that, it would really help if you had some basic idea of what the relations between the curves were, so that you could not be choosing curves that were dependent on each other. Okay, so here's a useful tool that our group came up with. So I'm going to define a matrix M, and I'm just going to take these symmetric F curves of the form Fi, 1, 1, and the last entry, of course, then has to be n minus I minus 2. I'm going to take those F curve classes and intersect them with the BJs, the symmetric boundary divisors. Okay, and then I'll let n be the inverse matrix of M. So here's an example for n equals 12. You can sit down with the Keough-McKernan formula and work out the entire matrix M, and then you can compute, n using, for instance, Macaulay 2. And you can see that there's a lot of structure to this matrix n. So for instance, let's look at the last column. 1, 3, 6, 10, 15. That's the sum of squares. 1, 1 plus 2, 1 plus 2 plus 3, and so on. The next column is doubled, and actually, sort of the upper triangle in that matrix is relatively constant. All right, well, what our group managed to do, we found a closed formula for this matrix n. Okay, I'll show it to you, but again, all I really have to say about it is that it's piecewise linear, and we found it. Okay? Here's why that's useful. So the first application is, if you have a symmetric divisor, and if you know its intersection numbers with the curves of the form Fi11, then you can obtain its class in the usual basis of symmetric divisors just by an explicit matrix multiplication. Of course, in terms of pure linear algebra, everyone always knew you could do this, and the point is we have the explicit formulas for it now. As a second application, if you give me any symmetric F curve class, I can write that curve class in the basis given by these 1, 1 curves, again, by an explicit matrix multiplication. Okay, so I can give you an explicit formula for how to write any one of these curves in this basis. And just to put this result in context, Kiel first described the relations among the boundary divisors on M0 n bar, and so you can think of our result as being sort of dual to the Kiel relations, but for symmetric curve classes. Again, I think I've got time to maybe show you an example. So yeah, let's run through an example now. Let's find the coefficient that I'll call gamma 3. So this is the coefficient on F3, 1, 1, 33. So here I'm fixed n equals 38. When I write the curve F3, 4, 4, 27 in this basis. Okay, so again, everything can be boiled down into some nice piecewise linear functions. You could probably give a description of this that's completely symmetric in the entries A, B, C, and D, but I actually think it's more useful to go ahead and just order the elements A, B, C, and D on your F curve. So suppose that we've arranged them so that they're increasing, and I'm going to define 3 functions as follows. The first one I call capital A, and again, I don't really have anything to say about the interpretation except that it's piecewise linear in the entries. And in our particular example, A, 3, 4, 4, 27 is going to be 0 because my last entry is really big, n equals 38, so G is 18. And so our last entry is sufficiently big to make this capital A equal to 0. Next, I'm going to define a really simple piecewise linear function f. You can think of this as a function that flips numbers. It either returns to me x if x is smaller than g plus 1, or it gives me n minus x otherwise. Okay, so where does this show up in birational geometry of m0 n bar? Well, of course, our boundary divisors, you have I points on one side and n minus I on the other, and I just always want to choose the one that's smaller. Okay, and the last function is, again, piecewise linear, but slightly more complicated. Well, what do? I sum over first the 4 entries A, B, C, and D, and the second summation is over B, C, and D. And again, I have just some explicit piecewise linear function, and let's compute that now. So Rs is equal to this. Okay, so S is equal to 3. So what do I get? So first I sum over A, B, C, and D. So there's 3, 4, 4, 27. And then I sum over B, C, and D again. All right. And what am I summing? Okay, I take my entry A, and I subtract 1 minus S. Here I get 4 minus 1 minus 3, 4 minus 1 minus 3. Here I have a 27, I need to flip it first. Okay, so I'll get 11 minus 1 minus 3. Then my formula says if this is less than or equal to 0, don't sum over it. Okay, so far my total contribution is a 7. Now, what about the second set of terms? I'm actually going to subtract some terms. And what are they? So here I take 4 plus 3, so I have 7 minus 1 minus 3. Same thing here. And let's see, I would get an 8 minus 1 minus 3. Okay, so I have minus 3, and minus 4. And so my final answer for all of this should be 7 minus 3 minus 4 minus 3 is a negative 3. Okay. And, oh, sorry, that's the answer for B, and then my final answer is I combine A and B. Okay, we just did that. All right, so we know how to compute, or we know how to write our F curves in a basis, which means we have an idea about what the relations between them are. Okay, and so here's two observations that help us prove that these divisors I started with are extremal. So first of all, they're often 0 on curves of the form f I k k, and then of course the fourth entry would be n minus I minus 2k. Not just for any k, but where k is roughly equal to n over j. So that's just an observation. Second observation is that if you fix an integer k, the family of curves of the form f I k k often has nearly maximal rank. I don't want to say they're always independent, but they generally have very high rank. As examples, when k equals 1, that actually gives us a basis of the symmetric F curves. When k equals 2, they're actually independent. When k equals 3, I think, like I said, there might be one relation, but still you get a family of high rank. Okay, so I'm going to define a family of curves. I'll call it curly F. You can think of this as our first attempt at a family. And it goes like this. I'll write my n as jk plus r. So in other words, k is the floor of n over j. And here's how I'll define my family. For I going from 1 to g, I'll take the 1, 1 curve fi1, 1 if I can. So if my divisor intersects that curve in degree 0, I'll take it. If not, then here's the thing I'll try to do second. If my divisor intersects fi1, 1 non-negatively, or sorry, positively, then I'll take the ikk curve if I can. And if I can't, then I'll take the ik plus 1 curve. Okay, and you can prove the following. First of all, whoops. Oh, sorry. Before I prove anything, let me do an example. All right, so again, let's take n equals 28 and j equals 11. That's something we worked with earlier. Then you can work out g is 13 and k equals 2. And we're looking for G minus 1 independent curves, so I need 12 independent curves, all of which intersect my divisor in degree 0. Okay, so let's start with I equals 1. I need to compute f111, comma 25, dot d. That's the example we did earlier, and we got a 5. Okay, so it's not equal to 0, so I can't pick that curve. So now I try again. I try f1kk, which is f122. Oops. Compute that intersection number. It's also non-zero. All right, so I need to try f1, k plus 1, k plus 1. So that's f133. And I finally get something that intersects my divisor in degree 0. So that's the curve I'm going to take. So here's my family f. So far, I know one curve. It's going to be f133. All right, so you do this for each I equals 2. Okay, we get a non-zero number. Keep going. Get a 0. We take it. I equals 3. Compute f311. It intersects our divisor d in degree 0. So we're done. We take that curve. Okay, so you run through the whole family like this, and you compute all the curves. And what you can show about this family F is that it always contains at least G minus 1 distinct curves, and they all intersect our divisor in degree 0. Then the proof splits into some cases. So if J actually divides N, then you can show that the rank of the family is G minus 1, which is exactly what you wanted. You're done. The divisor is extremal. Second case, if the remainder is positive and this number k is at least 3, then you can still show that the rank of f is G minus 1, and so the theorem works. But in the last case, if k equals 2, then it's easy to show that this family always has very high rank, but sometimes the rank can drop a little bit below what it needs to be. And so let's take a look at these families more closely, and we'll see what's going wrong, and we'll see how to fix it. So in the first case, so if r equals 0, so remember this is the case where J divides n, then the family is really beautiful. It's extremely regular. You get a kk curve exactly when I is congruent to minus 1 mod k, and the rest of the time you just get 1, 1 curves. Okay, so the kk curves show up in very predictable positions, and it's a very beautiful family to work with. All right, in the second case, so let's say J doesn't divide n, and let's say that n over J floor is at least 3. Then what you can show is that your family consists of curves of the form f11 and ikk, and it turns out you never need that third kind. You never need the I k plus 1 curves. And you stare a little bit closer, and you start to see some patterns. Okay, so how do the kk curves show up? Well, you can either have a pair of kk curves, so like this, then followed by a bunch of 1, 1 curves. Okay, or the second possibility, you might have a pair of these kk curves followed by only k minus 2 1, 1 curves. And then the last possibility is, well, you might have a single one of these kk curves show up, followed again by some 1, 1 curves. Okay, and all I have to say about that is it's this third case where you have a single kk curve popping up in the family that really makes the proof of independence pretty difficult. What about the last case? Okay, so now we have J doesn't divide n, and k is greater than, sorry, k equals 2, not k greater than or equal to 23. I apologize, that's a typo. Now it turns out that in general your family will require both 1, 1 curves, 2, 2 curves, and 3, 3 curves. And they show up in the following patterns. So one pattern I'll call a 3, 2, 1. Okay, so for some I, you have the curve I 3, 3. The next one's a 2, 2 curve, and then the next one after that is a 1, 1 curve. Another pattern that can appear is you might have 2, 2, 2 curves in a row. And the third pattern you might see is a 1, 2, 1. Okay? And again, remember, this was the bad case. These 1, 2, 1s can actually cause the rank of your family to drop, in which case this family wouldn't be good enough to establish the theorem we want to prove. Okay, so now that we're aware of these patterns, here's how you can define a new family G that'll do everything we want it to do. So we define a family of curves curly G. Again, think of this as the good family. start off with your family F, the first one. All right? Now, if you were in one of the first two cases, and if you ever had a single KK curve, what you should do is you should replace it by a pair by taking the curve right after it and switching that to a KK curve also. Okay, and you can prove a lemma that shows you can always do that. If you were in the k equals 2 case, what you want to do is go back to these patterns. You want to find any of the 1, 2, 1s that show up. Again, those are the bad patterns. And you replace those by 3, 2, 1s. Okay, fine, we're done. And the last thing, our family G right now actually has one curve too many. I'll tell you which one you should drop. Drop the last curve, which doesn't look like a 1, 1 curve. Okay, and then the theorem we proved is that this family G is a family of G minus 1 distinct independent curves that all intersect our divisor in degree 0, and that means that our divisor is extremal in the symmetric Neff cone. All right, I'm kind of running out of time, but let me just give you a hint as to how we prove this thing. All right, so I take my family G and I write out all those curves in the 1, 1 basis. Okay, so I get some monster matrix, but it has a lot of structure to it. Okay, so here's an example: n equals 38 and j equals 9, which means k equals 4. And again, you can see the rows in this matrix, which correspond to 1, 1 curves, look like rows and columns of the identity matrix. And again, we see we have a pair of KK curves showing up in some relatively predictable places. Now, of course, I want to compute the determinant of this matrix, but I don't need the whole thing to do that. Any row or column where I have something that looks like the identity, I can echelonize easily. All right, so I extract the submatrix of rows and columns that come from the KK curves. Okay, I'll call this matrix C prime. And now you're probably starting to see a lot of patterns to this thing. This lower right block is almost upper triangular. The left two columns are all the same in the lower rows. What I'll do, I'll take my last row and I'll use that to row reduce everything above it, and I'll get a really nice matrix. Okay, now it's upper triangular with ones on the diagonals, except possibly for the last row. Okay, so in all cases you get something like this. You have either 1 or 2 rows that you need to row reduce, and you can do that, and if you're clever about how you do it, you can actually get recursive formulas for the determinant and show that it's non-zero. Okay, so let me just mention some work in progress. We have shown that these determinants are always non-zero, but we realized it is actually not much more work to just compute them. Okay, and so the determinants of these matrices turn out to take on one of possibly 3 extremely nice values, and that also meant that I could check this theorem by computer, and we did that for n equals 6 to 150. All right, now in my last 2 minutes, I want to tell you a little bit about the morphisms associated to these divisors, which again, in my mind, is really the interesting question in all of this. And so I want to share with you some predictions that Noah Giansicurza has made. He's a graduate student at Brown, and I met him earlier this year, and he's working on the case of conics in P2, and well, we got to talking, and I said, well, you know, you should see if your divisors line up with conformal blocks ever. And so I gave him a bunch of data, and he came back and made these predictions for us. So I want to define a parameter space that I'll call RNC n comma D. And so this is going to be the incidence locus in the Hilbert scheme of degree D rational normal curves, and then I want n marked points to lie on my rational normal curve. I'm going to take GIT quotients, and here's the kind of linearization that Noah tells me I should use. I should put 0 weight on the Hilbert scheme side, and I should take symmetric weights on the marked point side. Then Noah is in the process of proving the following claims. First of all, there's always a morphism from M0 n bar down to these GIT quotients. And moreover, he believes that the pullback of the distinguished ample line bundle on the GIT quotient is going to be a multiple of this divisor dn1j that we started with. And let me just point out, it seems to me that if you were to just start with this GIT quotient and try to compute the class of this pullback on M0 n bar, I think that would be pretty hard. Alexeyev and I managed to do it in the case of SL2, but even for SL3, Noah still hasn't managed to do this. Okay. But thanks to our theorem, if Noah merely shows that this map is actually a morphism, and if he checks that it collapses all the curves in our family curly G, then that will actually compute the divisor class form up to a multiple. All right, so we're not just finding extremal rays. In some sense, this is sort of a computational tool to at least compute divisor classes of divisors which happen to be extremal. All right, I'll stop there. Thank you very much.